Hi, welcome back to another Lab in Theory video. I know it's been a while since I've uploaded any tutorials, but my hope is to be able to develop a series of videos, all of which center around the MNIST database of handwritten digits. By looking at this very popular database of handwritten digits, we'll be able to learn a little bit about data mining and various machine learning techniques. Now, if you're not familiar, the MNIST database is a very popular database which contains 60,000 examples of handwritten digits in 28 by 28 images. It also contains an extra test set of 10,000 examples, and it's sort of been the standard data set that you play around with when you're learning or developing a new data mining technique or familiarizing yourself with some machine learning. So in this video, which is the first of a series of videos I'll be uploading, we'll be looking at a dimensionality reduction technique called Isomap. Now, if you're not familiar, dimensionality reduction or nonlinear manifold learning takes high dimensional data, like a 28 by 28 pixel image, and it attempts to extract a meaningful embedding into a lower dimension, usually 1, 2, or 3, along which the data lies. Now, if this is entirely foreign to you, the concept of dimensionality reduction, I definitely encourage you to read up about PCA, and if you're familiar with PCA, then you can of course go to Wikipedia and read up a little bit more about manifold learning techniques. Again, I mentioned I'm using the Isomap technique in this video. I'm also going to be using Python. We're going to be using a Jupyter notebook. And so I expect you to have NumPy installed, Matplotlib, and scikit-learn, which we'll be looking up in a little bit. Now, back to Isomap. So what is Isomap? Now, this paper came out in December 2000, which documents this technique, and it really sparked an entirely new field or discipline, or maybe it didn't spark, but it popularized this discipline of manifold learning. So in this example, they developed this algorithm, Isomap, and what they do is they provide a couple of examples where they, in this example right here, they take a bunch of images of the statue, they perform this Isomap technique, so they project the high dimensional images onto 2 dimensions, and what they find is the first dimension here, the x-axis, correlates with a rotation of the pose of the statue, and the y-axis correlates with the position or the angle at which the statue is viewed. So down here, you can see we have sort of an up-down view looking down at the statue from the head, and as we go up, we're looking up at the statue from the chin. And the point of this technique is manifold learning is it's an unsupervised method. What that means is we don't actually look at any labels. We take the raw training data, the input, the x data, the independent variable, and we attempt to extract a meaningful set of coordinates that characterize something important about the data that we have. And you can see they repeated this example with a bunch of digits here, the digit 2, and we'll be sort of reproducing something very similar to this in this video. Now, feel free to check out this paper and just skim through it or read it if you're interested in a little more detail, but this video is going to focus on application. If you're interested in theory, you can always do that on your own time. Now, to get started, we'll download the MNIST database. There's the training set, both images and labels. So let's copy this link. I will download that, and then I'll copy this link as well. And we'll download the labels. Now, if we go ahead and list that, let me do that one more time. We need to unzip these. We'll use gunzip, train images, and then gunzip train labels. And then we have unzipped both of these files. Now, these files are in a binary format, but lucky for us, there's a very nice little simple GitHub gist someone put up on GitHub of a small function that will take the data out of these binary files and give it to us in a NumPy array. Now, I'm going to go ahead and make a notebook. We have our MNIST folder right here, and I've made a folder for Isomap because we will be applying different techniques in the different videos to the same data set. So I'll go to Isomap, I'll create a new Python 3 notebook, and let's give that a name. I'll call it MNIST Isomap tutorial. Great. Now to get started, we'll import a few things. We're going to need to import struct for that function. So let's import struct, import numpy as np, and then we'll import the manifold submodule from scikit-learn. We'll look at that in a little bit, but let's go ahead from sklearn, import manifold. And let's go ahead and import matplotlib.pyplot as plt, and then use the magic here, matplotlib inline, so we can plot things inline in our notebook, and go ahead and execute that. Great. Now, let's copy this function over. So go ahead and maybe I'll just click raw right here. I'll copy this function, and I'll paste that right here and execute it. Now, the next step is to actually import the data. Let's call this raw train. We'll import the raw training data. We'll use the read idx. My file is located directly above. We want train images. And let's go ahead and import that. Let's take a look at this data, raw train. You can see it's a collection of NumPy arrays. We need to process this data a little bit, but let's take a look at the shape. You can see we have these 60,000 entries as rows, and then we have another 2 dimensions, which are the 28 by 28 images. What we will be doing is flattening these 2 dimensions together. So we'll turn a 2D image into one long 28 by 28 vector. The reason for that is we need to feed in the information as a high dimensional vector and a number of sort of each column representing a feature, so the 28 by 28 columns, and each row representing a data point. So this is our raw data. Let's go ahead and just get rid of that. We will call it train data, and then let's reshape this. We'll use np.reshape. And we reshape raw train, and the new shape we want is 60,000, and then we want 28 by 28. We also want to import our labels as well, because we're going to use that in a minute. I did mention this is an unsupervised technique, but you'll see in just a minute why we're going to use that. So train label equals read idx train labels. Run that. Great. So now let's take a look at train data shape. You can see that's 60,000 by 784. And then train label. That's a NumPy array of just all of the digits that correspond to the observations in our training data. Now, when applying the Isomap technique, what we're going to do is actually take a subset of the digits. In this case, I chose to take a look at the digit 8. You can pick any digit you want. This is just an example, and this just makes this large 60,000 entry data set into a more digestible size, and we can really look for correlations and trends with just one digit. Now, how does this Isomap technique work? Well, scikit-learn makes it very easy for us. Here we have sklearn manifold Isomap. In fact, you barely have to specify any parameters. The default parameters are pretty good already. Nneighbors here defines how many nearest neighbors are going to be factored into the dimensionality reduction. Again, go to the paper, read up a little bit more about it if you're interested. And the other important value is n-components. How many dimensions do we want to extract? In this case, 2 is the precise number, in fact, that we're interested in. But what I'm going to do is I'm going to specify these explicitly just so we know exactly what we're doing and how we can extract them, or how we can modify them later on. Now, coming back to our notebook, the next thing you want to do is define our X data, which will go into the manifold learning. In that case, it will be train data, and let's just select out train label equals 8 because we want only the digits corresponding to the number 8. Our Y will be the transform data, so we'll go manifold.isomap, and we'll pass in, and again, I said these options aren't entirely necessary, but I like to specify them so I know exactly what I'm doing later on. And components equals 2, and then we can go fit underscore transform X, and go ahead and run that, and that will take our high dimensional data X, and it will perform a dimensionality reduction and give us Y, which will have 60,000 rows by 2 columns, the low dimension that it sort of extracted. So let's go ahead and run that. This will take a minute, so I will cut back in when this is complete. Okay, now that the isomapping is complete, let's go ahead and take a look at what Isomap has discovered for us. The first thing we'll do is go ahead and make a scatter plot. So plt scatter, and let's plot our two axes, y0 and y1. Let's run that. Again, you can see it's sort of like a blob, a spray of points. And what we want to do is to be able to correlate these two dimensions with some feature of the digit 8. And the way we're going to do that is we're going to create a grid on this data here and select some landmark points. So let's say select 5 approximately evenly spaced points in each dimension for a total of 25 points. So in order to do that, let's just define a new function. I'm going to call this find, let's say, landmarks. And we'll pass in y, which is our vector y here, our matrix y, and then n and m. Let's just make it a little bit general, and these are going to be the number of points that we want to select in this along this axis and this axis. So just to sort of repeat this to drive the point home, what we want to do is we want to select some points that are approximately evenly spaced along the x and y axis on a grid and plot the digits associated with them in order to see if there's any particular trend along these two axes that the isomap technique learned. So in order to do that, we're creating a function. We're calling it find landmarks. And let's define our x range, and that'll be equal to np linspace. So we're just going to linearly space some points, and we want to find the minimum of the first dimension. So again, we want to find this point right here, the minimum along the x direction, the maximum along the x direction, and then define some 5 evenly spaced points along this, or n evenly spaced points in this case. So we'll go np.min y 0 and np.max y 0, and then we'll say endpoints. We will copy this yr, so the y range. In this case, it'll be the first dimension here, or second dimension m. And these are our two ranges, and then let's grid these by using the mesh grid call is equal to np.meshGrid, and then we will say xr, yr. So this will create a grid for us of points that are evenly spaced. The next step, what we have to do is sort of select the nearest points from this data that lie along this grid. So again, we just create a grid here on this data range. And then we need to select the points, the actual data points that are closest to these, and just return the index of them so we can pull them later on. So in order to do that, let's define a list idx. Just fill it with zeros, and it will, the size of it will be n times m here. And I just put this in brackets to clarify what we're doing. We're creating a list filled with zeros. The list will be n times m long. Okay, now we have to do the little search. This might not be the most efficient way, but it gets the job done, so I'll go ahead and do it like this. So for I, x, y, this will be our index. This will be the x point and the y point. And let's just zip some data up. Range, n times m. So that will be the first I. This will loop through these two grid points sort of flattened, and then let's just flatten the data. So let's go xg.flatten. And then yg.flatten. And when we loop through those, what we'll do is find the closest point to them and put that in idxi. The way we're going to do that, we'll also force it to be an integer. So let's go int, cast it to an integer, because we're going to use these indices to select out points from a vector later so they can't be floats. The way we'll do this is we're going to compute the sum squared distance between a point and these landmark grid points. I've just called them landmarks here, and we'll use numpy sum and then np.absolute value of y, which is our data, minus np.array. So we're just going to define an array with x and y. Let's get our brackets straight here. 1, 2, and then we'll square it, because we're doing the sum squared difference I believe this should move out one more. A little bit confusing here. We got our sum. We also want to select actually it's important to specify the axis we want. So we'll go axis -1. And then we just want the minimum index, so that'll be argmin. And I think we're good to go. Then we will simply return IDX. Define that, no errors. Great. Now let's find our landmarks. So landmarks equals find landmarks y, and in this case I just want 5 and 5, so a total of 25 points. Run that, and let's take a look at what our landmarks look like. So we just made this scatter plot up here. Let's repeat that. And then we'll just plot right on top of that, plt scatter y, landmarks 0, y, landmarks 1, and this will plot our landmark points on top of our scatter plot. And what we can see right here is the landmark selection picked approximately evenly spaced points. This will be good enough for our use here. As you can see, we have an approximately even selection across the entire data. So what's next? Next is let's plot up the images associated with each of these landmark points. To do that, we'll create a new figure. So fig equals plt figure. Let's make this big. So I'll go fig size equals 15 by 15. Why not? And then let's loop over our landmark points. So for I in range landmarks, first thing we'll do is create a subplot so we can plot it up all in one figure. So this will be fig.add subplot, and then again we have 25 images, so 5 by 5, and then I+1 to select out the subplot that we are interested in. And then the image itself will be we'll use ax.imshow to display the image. In this case, we will need to reshape our NumPy arrays that we flattened back into 2x2 arrays, two-dimensional arrays. So we'll just do np.reshape x, and then landmarks, marks, and then the ith landmark. And then we want it to be 28 by 28 because that's the size of the original image. And we will also change the color, the default color for the IMShow, and we'll make it grays so we can just see the digits as they are. So that's going to be cmap equals, and we'll go plt.cm for color maps, and then get cmap, and then we'll just use grays. I think that's it for the image plot. Then, image plot. We want to actually interpolate as well. Set interpolation. Let me see if I spelled that right. Set interpolation. And what this will do is just smooth out the image so we can see it in a little bit nicer of fashion. And this will hopefully plot all of the images we are interested in. Let me just scroll back here, and then we'll go plt.show. Okay, let's run that. Okay, we made a mistake somewhere. Let's see. Set int. My apologies for that. Interpolation nearest. That's not how you spell nearest. Having a great day here, folks. Okay, let's see. Okay, it's complete, and this is the final set of data for the landmark points that we have. Now, what do we get when we take a look at this data? Well, just looking at it here, we can see that going from left to right, the tilt angle on the 8-digit sort of goes from being tilted towards the right to being sort of centered to being tilted towards the left. So it seems to have learned along the first dimension the tilt associated with the digit being written here. So the 8-digit tilts left to right. If we look up to down, we can see that the digits up here have a greater asymmetry in the loops of the 8. So this circle is much larger than that one. You can see these are approximately the same size, but as we move up, they are disproportionately large in terms of their upper, or in this case, a little bit lower loop. Also, they seem to open a little bit more up here, but we have some digits that where the loop isn't closed for the 8-digit. But I would say left to right, the tilt angle changes very clearly, and bottom to top, it looks like the digit is more asymmetric. So the 8 has a large loop and a small loop compared to the ones down here. And I know the dimensionality reduction isn't perfect, but it will find a general trend. In this case, it seems to be pretty strong, the tilt from left to right, and a somewhat weak but still apparent asymmetry in the two loops or the two circles of the 8 going up to down. Now, this is pretty much it, folks. I think what we've done is we've gone through, familiarize ourselves a little bit with the Isomap technique, and actually went through an example. We took the 8-digit from the MNIST database and performed Isomap on it, and we saw that we can use a few functions and calls from scikit-learn and NumPy to actually take the data and perform a nice bit of dimensionality reduction on it. Again, I hope you found this video useful. Thank you very much for watching. If you like this video, please give it a thumbs up. If you love it, please subscribe, and please stay tuned for more videos. Once again, thanks a lot, and I'll see you in the next one. Bye.